we're going to talk about Elasticsearch. We're going to talk about the HTTP client. This is the agenda nowadays. So I have a demo that is also up on GitHub, so you can just clone it and play around with it yourself. But we will walk through the demo, which is super small, basically all about JSON serialization from data that is returned by Elasticsearch. And on top of that, we just will fill the beginning minutes with a little bit of background and getting up and running. And most of the presentation is code as well. You might have seen this picture every now and then, just to make sure that you understand where we are. I think most of you already know Elasticsearch, which is kind of the heart of the Elastic Stack. The Elastic Stack is a set of products or different tools to basically solve arbitrary use cases if you want. Elasticsearch being the center of this, being the data store, being the engine that gets queried, being the engine that analyzes the data, crunches it if you need to, and then sending it back to your clients. And you can run Elasticsearch all by itself. Everything that you search on Wikipedia, for example, is run against Elasticsearch. And running Elasticsearch in there means you probably don't need any other of those products if you just want to use the index and search capabilities yourself, as Elasticsearch is an HTTP-based service. However, there's Kibana, which used to be a dashboarding tool. Nowadays, it's more of a dashboarding and monitoring and management tool, which is kind of the window into the stack if you want. So you have an easy-to-use UI on top of that. And the two products at the bottom are basically ways to ingest data into Elasticsearch. Of course, you can do all of this yourself just by using an HTTP client and connecting against Elasticsearch. But if you start collecting machine-based data, metrics, anything in the observability space like APM data, you may want to make sure that you don't write this kind of code yourself, especially with all the different ways of error handling. And this is basically where the beats come into play. The beats are very small, specialized tools that do one job and do it really well, and then send the data off to Elasticsearch. The most common beat probably is a file beat, which doesn't sound super fancy because it's basically tailing a set of files and sending the events over to Elasticsearch. But if things like log rotation come into play, remembering where you stopped reading to pick things up again, things with files, especially on different operating systems, just get much more complex. And Logstash on the right-hand side is not a small specialized tool, but more a generic tool. I consider it kind of a Swiss Army knife for ETL. You configure a certain set of inputs, massage, change your data, and then send it over to Elasticsearch or another set of outputs. So what we're going to see today is basically just the need for Elasticsearch, and then we have Java code that directly communicates with Elasticsearch using the HTTP client. Just a quick reminder what Elasticsearch is in a couple of seconds. So Elasticsearch is a search engine on top of all, and you can solve different use cases with a search engine. You have this classic full-text search use case, which basically allows you to do something like Google. You search for a term, you get back the documents where the term was found, right? This is what Google does. The fancy part is in the scoring and ranking, of course. But the next use case would be something like analytics. Again, you probably know this from many e-commerce sites. If you search for something, take a new TV, for example, then suddenly on the left side, you have a list of brands for the different TVs. And then you can select based on the brands. And this is kind of the first step of analytics, where you start grouping the search results based on criteria like the brand name or the category. What else is Elasticsearch? You can do geo searches, and one of the nice parts is you can kind of combine all of these categories. Elasticsearch is a distributed and scalable system. You can run it on a single node. You can run it on hundreds of nodes that form a cluster. It has the ability to detect node failures by itself and act accordingly, like making sure your data is copied around the cluster without you having to interfere or intervene. The base interface there is HTTP and JSON, just because most developers know the protocol as well as the object notation, so it's easy to deal and handle with. And it's kind of the center of the Elastic Stack, but we already saw that before. So Elasticsearch has been around for a long time, and also Elasticsearch HTTP clients have been around for a long time, especially in other languages like the Perl and the Ruby client. They existed before the company around Elasticsearch was actually founded. So they've been around since like basically 2010. And that was for those two languages. But for Java, there was a long time no HTTP client. And the reason for this is that you could basically reuse the client that was also internally used for the node-to-node communication. That was called the TransportClient. It ran on the port 9300 and also had its own serialization. So it wasn't an HTTP client, but using the binary protocol. That came with a couple of problems, mainly around like backwards compatibility and serialization of this custom protocol over the wire. And also you could not really differentiate, do I have a client connecting here, or is this another node for node-to-node communication? And just by splitting the communication across the two ports, this became much easier. The good thing is you had all the query builders available, all the POJOs that were already or have already been used internally. And so over time, the idea came up to write a real HTTP client, especially to split this up between client and node-to-node communication. So nowadays, we basically have this HTTP client. It depends on the Elasticsearch core project. So you will drag in a couple of dependencies in there. And it's based on the Apache HTTP client. I think that's the most important part here. This also means it works on Java 8. It doesn't really matter what JVM you're running on Elasticsearch. This one is running on Java 8 and up. And it supports synchronous and asynchronous calls. That's maybe one of the more important implementation details here. So you can run it in a blocking environment, or you can also run it in a non-blocking environment using a kind of listener-based strategy. The implementation is thread safe. So if you have an application like Spring Boot, only need to instantiate a single client. That might be an important thing, especially because the client itself internally will use a couple of threads. So it's just important to make sure you don't run an arbitrary number of threads within your application, and you don't create a new client for a single call and then close this client again, because this is going to make your application really slow. There's a REST client. Basically, there are two clients. And one client is used for the low-level communication, if you want. That one's called the REST client. And one is used as the high-level client, which contains all the builder classes and all the representations of your request data as POJOs, as plain old Java objects. That will just this implies that you don't have to hand create any JSON data yourself when you send out a query, but you really can just use Java classes and helpers to produce such a query. Yeah, this is basically what it looks like. You would usually instantiate a REST high-level client. That one internally uses a REST client. You could also hand over a custom REST client. That's the low-level one. And within the REST client, we are basically using the Apache HTTP client implementation. So what are the responsibilities? Why do we have two different clients? First, it was basically also easier to get up and running, to first come up with a client that just did the bare bones communication, and then put another client on top of that, because we basically had a kind of multi-step approach. When we first started the client in Elasticsearch 5, we basically only had this low-level client, and then we put the different classes on top of that. And the low-level client is responsible for things like the TLS setup, basic authentication, sniffing, and node selectors. We're going to talk about that in a second, what this is. Where the high-level client basically has concrete request classes for all the different endpoints. It has builders for all the different queries and aggregations, so that you don't have to deal with JSON, basically. Yeah, one last word for compatibility. I already talked about Java 8, but of course, that's not everything. We also have to talk about the compatibility talking to different Elasticsearch clusters. And in this context, it's important to note that this client is supposed to be forward compatible, which means when you have the REST client in version 7.1, then you should always be able to communicate using this REST clients with higher versions. So you should be able to talk to Elasticsearch 7.5.1 or 7.6.2, which is the most recent version. That said, of course, it mostly makes sense to also upgrade the REST client over time when upgrading in the S cluster. The good thing is you don't have to do it at the exact same time, but it still makes sense just to catch bug fixes, just to probably expose newer endpoints that have been added over time. And of course, you also may want to monitor breaking changes over majors. So if you have a really old client, you want to make sure that this one gets upgraded as well. And one thing that, because of the forward compatibility, makes most sense, you upgrade the client last. So basically, you do an Elasticsearch upgrade, and only after that, you would upgrade your application. So how does this look like from a code perspective? Basically, you only need to instantiate the REST high-level client in the first line. The reason for this is that this implicitly instantiates a REST client internally that then also gets closed when you close the high-level client, and you specify the endpoint. In this example, we would specify a localhost 9200, so the kind of standard local configuration. And then you have two ways to retrieve your data. The second line here shows a synchronous request to retrieve the cluster health, and the third line and the follow-up uses a listener, which then gets basically appended to the health async method at the bottom in the last line, which then makes everything here async using an IO thread within the Apache HTTP client. And these are every endpoint basically has these two methods. You have one endpoint method, and then you always have one async method that you can use. One more thing you see here is the request options default. That allows you to add custom request options like headers, for example, if you would like to change the authorization on a per request base because you have a tenant-based app or anything like that, then you could change this here, or adding certain parameters if you want. So if you want to, or if you need basic auth, which hopefully you do, because you should not run Elasticsearch in an unsecured fashion, then we basically reuse the classes of the Apache HTTP client, which is called a credentials provider, supporting arbitrary authorization, and the basic credentials provider, allowing you to configure a username and password for this one. And you would use this credentials provider when you build the REST client. So this is something you can't change during runtime. Yeah, TLS and SSL basically has the same, not sophisticatedly simple way in Java to be configured. You basically have to load your trust store and your key store, and out of these different stores, you create an SSL context, and the SSL context would then be handed over for the HTTP client builder. So this would be the way to support custom certs, which probably are running on your own CA that is not verified in the bundled Java certificates. So let's get to indexing. So how do we get data into Elasticsearch? So in this example, we instantiate an index request. We point it to the index that we want to index to. You can set an ID optionally, but the last step would be that you have some object or POJO that you manage to serialize into a byte array. And then you can specify this byte array in the source method in the fifth line over here. And then you call client index, and then the index request gets sent up to Elasticsearch. In this example, I just assume that you have a nice method to create a byte array from a POJO, which usually means invoking an object mapper. And for the samples demo I use Jackson, which from my perspective is kind of the most used JSON serialization library. But of course, there are others like JSON and a couple more, especially in programming languages like Scala or Kotlin. So as you probably know, single document indexing is not really effective from an Elasticsearch perspective. So if you have high index load, you should always use a bulk request. The basic idea of the bulk request here is basically just to group several index or several write requests like index, update, or delete into a single request, and then send this one off to Elasticsearch. So in this example, we basically send 3 documents to Elasticsearch at once. Of course, this is also not optimal, but it works most of the time. But one thing you should consider is using a bulk processor, because we always tell users of Elasticsearch that you should limit your bulk requests by some criteria, like the size, for example. Your bulk request should not exceed tens of megabytes, like 10 megabytes or even 5 megabytes to begin with, or even 1 are actually a good idea, and then like going higher slowly. And at some point, you will see that your indexing rate gets slower because the bulk requests are too big. If we go back to the bulk request here, you don't have any good way to actually check for the size of bulk request. You could probably check for the number of documents, but again, this adds some tedious overhead. And one thing you can do is basically use the built-in bulk processor for that. So the bulk processor allows you to just basically dump documents to this bulk processor, and at some point the bulk processor decides, oh yeah, now it's time for indexing, and will send off a request. There are a couple of other official Elasticsearch clients and other programming languages which support this as well, like JavaScript or Python. So this is a really neat helper. And the way it looks like is basically like this. You create a bulk processor, you specify the client, second line, and then you have a listener. And the listeners are basically invoked before a single bulk request gets sent, after a bulk request returns, or if a bulk request returns but has a failure. For example, there's a connection failure to the Elasticsearch cluster. And you can also configure the criteria when a single bulk request should be sent off. So in this example, we configure this to be after 10,000 documents or after the complete size of a bulk request would exceed 5 megabytes, or if 5 seconds, no indexing, or it's after 5 seconds if they're new documents. So even if within 5 seconds, only one document is basically added to this bulk processor, it would be sent off. Yeah, the idea is that one of those 3 criteria has to match in order to trigger a bulk request. And then we have the concurrent request, where we can basically configure how many requests should this bulk processor be able to send in parallel. This is one request in parallel, so you can add new documents while a single request is running in the background. But of course, if the single request is still running and one of the bulk actions is hit, it would basically block to retrieve or add new documents in there. The last part is the backoff policy. It might be the case that the bulk processor cannot reach Elasticsearch or gets an error message telling you to wait, like when the Elasticsearch thread pool is already filled up. And then you can configure a backoff policy, how to retry. And there are different things like no backup policy, a linear backoff policy, or an exponential backoff policy, which basically means whenever you wait, you just wait a little longer. So you allow Elasticsearch to recover. All right, that was bulk processor. One of the disadvantages of the bulk processor, of course, is the fact that this is asynchronous, which means you don't get an immediate feedback for your document. So if you have some sort of CRUD UI in your application and you save a document, you use a bulk processor for that, you don't really know exactly when this document will be stored. And it highly depends on the application if you can deal with this or not. If you need this functionality to really know when the document has been stored, you could either use a single document index operation with the refresh set to true, or with a refresh value set to wait for, so that the request only returns once the document is made available for search. Search requests can also be sent. So you can see here that we have an input search, which we call my nice query. That will be what the user is typing into search box. And then you can see in the 4th line that we are using a multi-match query from the query builders class. So again, you see here, there's no need to create any JSON by yourself. You just specify you want to run a multi-match query, and that's about it. Then you send off the search request, you get back a search response in the 6th line, and you can just see, okay, if I don't get any hits back, I can probably return immediately. And once we get hits back, we probably want to do some per hit processing in order to create a POJO out of each of the hits that have been returned by the Elasticsearch search. So there are a couple of builders in order to create queries. Most of them for a query will be found in the query builders class. We're going to take a look at that in a second. We also have builders for aggregations or pipeline aggregations. But Elasticsearch is modularizing some parts internally. It uses so-called modules, which you can see when you start Elasticsearch. And there's a couple of modules that basically have their own query builders because they are not part of the core. So if you sometimes don't find a query, it's still very likely that it's somewhere in the high-level REST client, but you just have to figure out the right class, and it usually works by figuring out the query name, like rank feature, and then searching for a rank feature query builder in your IDE. Yeah, you can also use the from and the offset. Well, the from is the size one in Elasticsearch, like you would do when you write a regular query. You can see here there's a search source builder from and a search source builder size. Apart from that, the query is exactly the same. So you can do this with pagination. You can also do a mechanism called search after. I'm going to skip this one for today, what this is doing, but you can check it out in the sample implementation as well. All right, let's quickly talk about some low-level REST client features and then go to the demo. The first one is the node selector. And this is basically the point in time where the REST client differentiates from a regular HTTP client because it has some added functionality which is tailored to Elasticsearch. And a node selector allows you to select which kind of node you would like to connect to. So if you, for example, use the ingest node for all the documents you're indexing, it doesn't make a lot of sense to send data to data nodes that don't have this ingest role, because internally Elasticsearch would redirect this. But you can just create a node selector that only sends data to ingest nodes. And this is basically what this node selector is doing. You could also create a selector that only sends data to data nodes, or become fancy and check a couple of very different things in the node, like the node name or whatever. Just make sure you don't create a single hotspot in this context. The next thing is sniffers. Again, this differentiates you from a regular HTTP client. The idea of a sniffer in the REST client is that there's a component running in the background constantly polling Elasticsearch, I think once per minute by default, and it basically figures out which nodes exist and uses those nodes to send queries and index operations to Elasticsearch, and uses those nodes to round robin automatically. So even if you grow your cluster or you shrink it, you don't need to be worried about it, because using a sniffer in your HTTP client implies that it over time will send data to all of the nodes within your Elasticsearch cluster. Just be wary, this is an own dependency, so you have to add this implicitly. And yeah, basically this is how it works. You just create a sniffer builder with the REST client you created, which also needs to be closed. And this sniffer is doing all the work in the background to dynamically update the endpoints within the REST client. All right, a couple of things to consider in mind, to take into mind. You may want to use shading. The reason for this is that the dependency like Elasticsearch has, like Jackson or the Apache HTTP client, are used in many, many other projects, and you want to make sure that you don't have any version clashes, and that's something you can achieve with shading. The client is modular, so you may want to check if you have to incorporate another dependency, which need to be checked. And there's another useful feature, which is the strict deprecation mode. This is something that I don't think any other client in Elasticsearch has so far. So we have the notion of deprecation warnings in Elasticsearch, which are emitted in a log file. You may have seen the deprecation log, but they are also emitted as an HTTP response header. So whenever you're using a feature, maybe in a query or how you index your data, that will go away in one of the next major versions or in the next major version, you will have a header being returned telling you this, or you will have a log entry. The problem is that, of course, we all don't need read all the log files all the time. But with this feature, which we could just enable, for example, in our CI, the REST client would throw an exception if a deprecated feature gets used. This way, you can actually ensure that before you upgrade, but just setting this flag in your tests, that you don't use any deprecated features. So the strict deprecation mode is super useful for testing and figuring out before going into production if there's anything coming up when you do a version or a major version upgrade. And of course, if you want to use Elastic Cloud, you can basically use the Cloud ID to connect to Elasticsearch. There's no need to use this one single endpoint host name that you can figure out yourself. Just copy paste the Cloud ID of the stack you want to connect to, and that's about it. All right, if you want to debug and log, Apache client uses JCL, Java Commons Logging. I think it's now called Apache Commons Logging. It's been around for ages. You can set the Elasticsearch client package to debug for more logging. You can also set it to trace to see the whole HTTP request, but that one might contain authentication or authorization information like the username and the password. So be really careful with that, especially when putting it on in production. It also produces a lot of data. All right, let's take a look at the demo. I will use test containers. The code is on GitHub. So you can see over here, there's an Elasticsearch REST client samples. If you want to follow it, let me put it in the chat. So you should see my wonderful IDE now. Let's close everything and start fresh from nothing. And the idea here is that I basically have a product service that runs against Elasticsearch that allows you to find a product by ID. It allows you to execute a search. It allows you to paginate through the results. Every search just returns a page. And of course, it allows you to save a product. So the next thing we probably would like to take a look at are the tests for this. So when we go up here, I have an Elasticsearch test. This one is actually testing the product service implementation. And you can see here that it's using test containers. It uses the most recent Elasticsearch version. So what happens here basically is that the test containers library starts a Docker container, and you can use the Docker instance of Elasticsearch to run tests against it. So you have real integration tests running against a true instance of Elasticsearch, and you don't need to mock away anything. On the other hand, obviously you have the overhead of having Docker running, and starting and stopping Elasticsearch within the Docker container will add a couple of seconds to your tests. So most of the time you may want to make sure that you also have fast running unit tests. For example, in order to test that the serialization works, there's 2 serializer classes and 1 deserializer class, which is from Jackson. You would like to write that into a unit test and not test this completely against Elasticsearch. All right, so what do we do here? We start the container in a static method. So we want to make sure that the Docker container only gets started once for all the test runs. Otherwise, the tests will become really, really slow. We're going to connect to the mapped port. So the Docker container gets a mapped port, which might not be port 9200, which is only the running port within the Docker container. We set a node selector. We create a high-level client. And the product service implementation basically uses this client. We could also just run against a cloud instance by configuring a username and a password, and also by configuring the cloud ID, what I just showed. So if you want to use a Elastic Cloud instance and run this project as well, just uncomment these lines of code and see that it works. At the end of the test runs, we would like to close the client. And before each test run, we basically delete the index for the products to make sure that we start clean again. This example is basically just running a cluster health request. We want to make sure we don't have a red cluster. It's basically just to show the sync and the async project, the async calls for the HTTP client. So here it gets more interesting. So I have a small helper method called create products, which at the end creates me a product. My product is a simple POJO, which consists of 5 fields: the ID, the name, the description, the price, and the available stock. And when we take a look at the product serializer class, you can see that the ID is not written to the JSON document, because the ID is the metadata of the product. It's the ID that is used to identify the product. All right, so we're going to create a product. We're going to set the ID to null, because I want, like, to Elasticsearch have this setting this ID. And when I save the product and I get the ID back, the save method basically assigns a freshly created ID back here, and then this ID is not null. I also would like to make sure that I can store a product with a custom ID. So this one is running this test. And the next step will be to find products by ID. As you can see here, we create 3 sample products. We're going to save them. And now it's slowly getting time to take a look at the different implementations. So this one takes a look at the product service implementation. You can just save a list of products using a bulk request. You can also save a single product, which in turn will create a single bulk request. So internally, we use bulk requests here. The important part here is that a single index request is basically running exactly the code that you saw earlier in the snippet. The important part over here is the object mapper that basically creates a JSON data out of the POJO by using this product serializer. So this will be the object, starting a JSON object, writing a string field, writing 2 numbers fields, and writing the end object. Okay, the next step would be to execute a search. In this example, we basically create 10 products. We refresh the index, and then we run a search for 9. So somewhere in the description of the product, there's the number or the ID of the product from 0 to 9. And what we do here is we're searching for the string 9. We get back a single document. We ensure that the size is 1. and that the ID of the product is actually the product we expect. Going into the product search method from the product service, we can see here that we create a search request. And this is basically, again, using the high-level REST client. We do a multi-match query here, and we attach the query itself to the so-called search source builder. And this search source builder then will become a part of the search request. So the search request will be sent over here. That's the create page method. That one is invoked on every search as well. And I basically just have a shortcut here. If there are no hits available, I return something called an empty page to easily indicate, okay, there were no results. If there are hits in my response, again, we're going to read the value. We're going to create a POJO out of the underscore source field. But because it's only the underscore source field, we have to set the ID manually because the ID is not part of underscore source. You could change this behavior and probably also store the ID as a field in Elasticsearch. Then you would not have to do this step every time. But you would still have to ensure that the ID in the JSON body is the same than the ID you're referring to as the index metadata. Going back to the Elasticsearch test. So this is a search. I'm also returning a page here. The page is used for pagination because it contains the information like the offsets, the from, and the size. If you had a web application behind that, you would, of course, still need to serialize this information back to the client. It's just a bit easier in this example because there is no web application, but you would need to encode this so that the user can actually paginate through the system. Yeah, there's a pagination sample here where we basically use the next method. The interesting part of this implementation using next is that the caller himself doesn't need to know how pagination is actually implemented, right? This could be a scroll search, this could use search after, or whatever. You just specify a page object and then run the next search. And this is the reason why I opted for this design over here. Yeah, I also use search after. I think we can skip that in the sake of time. This is an example for the bulk processor, just to show you how it works. We have the listener here that is not doing a lot except putting the state of a response into the map. You can see here, you can also configure the concurrent request to 0, which means that the bulk processor will basically block the moment that one of the criteria, like in this example, hitting 10 documents is met. And yeah, this is the bulk processor API. We just add another index request one after the other. And at some point in time, the bulk processor will kick in and send data to Elasticsearch based on the criteria that we configured over here. This is a query builder test. So you can see here that I just played around a little bit around with how you can write your queries, because again, it's already takes some time to get used to this in Elasticsearch. So it also takes some time to translate this knowledge over to Java. And you can see here, we have a bool query that consists of a must clause. So we really want to make sure that a book is contained in there. We want to make sure that the stock is greater than 0, so that a book is on stock. And we want to make sure that the price is also greater than 0. There shouldn't be any free book in our data. And if the price is less than 100, we would like to boost this document. So in this example, if we take a look, this one document would be boosted based on that criteria. Yeah, this is the way how to write aggregations, and then we're going to return to the Q&A part of this. I just want to make sure that it's not only about full text search. You can also create your own aggregations. So we have our aggregation builder here to create a histogram aggregation. In this example, we would basically create a histograms for the price. So every 10 euro or dollar or whatever currency you are in, you would have an own bucket where the documents would fall into. And for each of those buckets, I would like to figure out what is the average stock that I have just by having an average aggregation on the stock available field. And yeah, this is the response. You can see here that there's a histogram class or a histogram object that you can extract by response get aggregations get prices to. You see here that the name is the same. And then we just walk through each of the buckets and collect the average value. And the last step is to make sure that the average value only rises over the buckets. The reason for this is that this was the way how I created the products. In real life, you would not do that, but for testing, it was sufficient. All right, so if you want to figure out more, especially if you want to see how the product service implementation looks like, just check out the GitHub project. If you want to know more about test containers, because it looks so simple here, which it indeed is from a user perspective, but it still makes sense to take a closer look at test containers in general. Take a look at testcontainers.org. It's over here. There's a couple of different systems. Let me see, where is it? Yeah, there's a couple of different modules for different endpoint systems like Elasticsearch, Kafka. You can also configure your own custom Docker containers if you want and start those up. That might make sense if there's anything you extend from the official Elasticsearch container. So it's rather flexible. All right, let's do a quick summary. Yeah, one of the things I always tell people is to think async. Many applications nowadays have sort of an asynchronous mode, even in the web space, just to make sure that they don't burn any resources or unrunning threads and that they don't block while waiting for I/O. So you should probably do the same. Think of sniffing once you run in production. Take a look at the documentation. And yeah, this is just something to keep in mind. If you use Elastic Cloud or run against any other cloud provider, it might make sense to also have another system there where you can just run the tests again to make sure that the implementation behaves exactly like it would on a local system. All right, wait, let me quickly share blog post later. But yeah, if you want to test out Elasticsearch, you can run it on yourself. You can run it on the test containers Docker container. You can also use Elastic Cloud in there, which basically is on our Elasticsearch or Elastic Stack as a service. You can see it starts at $16 a month in the smallest tier. There's also subscriptions offering you more than the free and basic tier if you need certain features. And if you need more help, and this is the most important part for me, check out the Discuss forum. It's discusselastic.co. You can just open it over here. And you can see that there's just a forum for a ton of different products that we have for all the different solutions like APM, logs or metrics or uptime, so part of the observability, like for security and SIEM. So everything that you can solve or every product that's there and every solution does have an own forum. My biggest ask here is if you use a forum, make sure you write a proper issue, make sure there's an ability for the readers to reproduce your problem, because this will just speed up the way of answering a lot. And there's lots of developers in the forum trying to help, so don't hesitate to use it. And also lastly, I'd like to talk about community at meetups. You probably know this as you're here. There's Community Elastic.co. Right now, there are basically a couple of virtual meetups. They're sort of grouped by time zone. This is the EMEA one, but there's also one for the Americas and for APAC. So take a look at that one. And yeah, that's that. There's also official Elasticsearch training. And now we have time for Q&A. So if there are any questions, where is Elastic Cloud running is one question that was being asked. So Elastic Cloud runs on a bunch of different data centers and cloud providers. You can specify this when you create a new instance. So you first specify I want to run on AWS, Azure, or GCP, and then you specify the region. So I want to run on AWS in Frankfurt because of legal obligations. That's a very common thing in Germany, that the data doesn't leave German jurisdiction. And that one can be specified whenever you set up an instance of Elastic Cloud. Do we have similar clients available for other technologies like PHP and Python? Absolutely. Let me quickly share the link, because I think I skipped over it. There's a dedicated clients documentation section, and it is this one. So the interesting part of these clients, for PHP, Python, Go, there's a better one in Rust. There's Ruby, there's Perl, which is, I think, not too well maintained right now, to be honest. But on the other hand, it doesn't need a lot of maintenance, which is a good thing. There's PHP, there's .NET. And the .NET one also has kind of this high-level client implementation, so you have your own classes for creating this. And the interesting part of all of these clients is basically that we use the same tests, which means we have a set of YAML and JSON-based testing specs in the Elasticsearch project. And in order to make sure that all of the clients support those features in there, they run the same test suite and they pass the same test suite. That's also one of the advantages of the official client. We all know that they are up to date with the latest Elasticsearch changes, or we all know that they are being worked on. So you can, of course, also reuse this client spec in your own community client if you want, so there's nothing blocking you from that. But we just wanted to make sure back then when we started this client initiative that the clients are on the same level and that they're basically just small additions, or that they kind of bind to the programming language, that they follow the principles of each programming language. Like the Python is very different to Ruby in that regard. And that was one of the criteria of this clients as well, but they all should support the same feature set. Are there some search features? No, I think from a search perspective, we should be on par there. Like, this is the search in bulk or search and write operations are the two most important requests, or the couple of most important requests. And the search features should all be available in the high-level REST client as well. If not, it's a bug, and we have to fix it. Yes, thanks, Philip. That's a valid point as well. What you can always do is specify an endpoint and send your own custom JSON or your own custom raw data there. That's true.
I think that also ties into the question above from Nitin, that there was one above, which also ties into the high and low level client question.
I understand that we usually call the high level client as indicated in the demo. What is the difference? Yeah, exactly. So most of the time you use the high level client because we have dedicated methods for all the different endpoints mapped in Elasticsearch. But if there is, for example, any bug, or you have an old client that doesn't support a new feature, you can just use a low-level client and send a regular HTTP request and configure it all by yourself, like sets the headers like you want, these kind of things. Is it possible to do a partial update on nested objects without using script? As you cannot properly specify this in the doc object of an update request, you would always have to do a script, like removing a whole element, for example, is something you can't do. But if you specify the whole nested block as part of a doc part in an update request, you could do that. And this would work independently from the high-level REST client. If it works in the HTTP request, it will also work in the high-level REST client. Does Elasticsearch enforce timeout correctly internally if it is set in search highlight request? If you're referring to the search timeouts, then this parameter is just passed over to the search and it will be respected. Is the Elastic index data stored inside cluster nodes or any other way? If that's the case, how to avoid data loss in case of node failure? So the basic idea of this is, again, completely independent from the high-level client, is just to have more than one copy of your data available in the cluster. And if a single node fails, you still have a copy. And based on this copy, you can also create another copy, right? And this is how you would sustain a node failure. This also implies that you can only sustain as many node failures as you have copies in your cluster, but that's usually a trade-off you're willing to take. All right, that's it. Thank you, and see you next time.